Another important theoretical probability distribution in medicine is what's called the Poisson distribution. Like the binomial distribution, it is also a discrete probability distribution. It was named after the French mathematician Simeon Poisson, who derived it and first introduced it in 1837. This type of probability distribution gets invoked when the outcome is the number of times an event occurs randomly in a given time or space interval, instead of whether or not an event has occurred. It is likewise invoked when the event one would like to determine the probability of is rare. The Poisson distribution is said to be a special case of the binomial distribution when the number of Bernoulli trials becomes very large and the probability of success, or P, is quite small. So if we stuck to using the binomial distribution formula for this, a large number of Bernoulli trials will mean we will end up with a very large number of possible combinations that perhaps our calculators may not even be able to handle. Now, let's look at how the outcome is described. Take note that the outcome is actually count data or frequency that occurs in a given time or space interval. We will be able to appreciate this more with the example a few slides from now. So let's say a random variable x has a Poisson distribution. The probability then of exactly x occurrences is given by this formula. In the Poisson distribution equation, the random variable, which we denote as x, refers to the number of events in a given time or space interval. Unlike the binomial distribution, in which there are only a finite number of discrete values that x can take on, in the Poisson distribution, x can take on any discrete value ranging from 0 to infinity. The lowercase e here is a very well-known mathematical constant called Euler's number, which has a value of roughly 2.718. Lambda here, on the other hand, is the mean number of events per interval. It is what's called the parameter of the Poisson distribution. If you could recall from the binomial distribution video, link in the description, you only need the values of n and p in order to describe the binomial probability distribution. In the case of the Poisson distribution, you only need the lambda to be able to characterize the probability distribution. By the way, the mean and the variance of the Poisson distribution have the same value, and that would be the lambda. Just because the Poisson distribution is used to determine the probability of rare events, it does not automatically mean that all instances that invoke the use of the Poisson distribution are nothing but rare events. Actually, the rate that such events occur over a given time interval, which is the lambda term of the Poisson distribution equation, can be any number. Recall from earlier that the Poisson distribution becomes applicable when the outcome is the number of times an event occurs over a given time or space interval. And just because the Poisson distribution is applicable in this case, it doesn't mean right away that this said event is rare. That being said, there are numerous fields in which the Poisson distribution finds application. In medicine alone, it already has many applications. One would be to work out how many births would be expected per night in a maternity hospital. Another would be to determine the number of genetic mutations occurring on a given DNA strand per unit time. And then we have understanding rare diseases such as certain hematologic malignancies. As with any probability distribution, the Poisson distribution also has a set of assumptions that must be satisfied. Number one, the events of interest must be independent. Now that you've finished watching the video series on the fundamentals of probability, this statement should be pretty self-explanatory at this point. Number two, the events of interest occur at a constant rate. That rate is actually the lambda. Now, recall from a couple of slides back that we defined lambda as the mean number of events per time or space interval. So, if we have a time unit in the denominator, like per hour or per day or per year, then we have what's called a rate, hence the use of that term in the statement. Now, in relation to this, for any length of time, which we denote as t, we would expect to see, on average, a constant number of events, and that number is equal to the product of lambda and t. Now, another way to regard this assumption is that the probability of a single occurrence of the event in a given interval is proportional to the length of the interval. The longer the time interval is, the more likely that a single occurrence of the event will take place. Now, lastly, the interval has to be fixed. Now, if this time interval happens to be very, very small, it becomes highly improbable, essentially zero probability even, that more than one occurrence of the event takes place. I'll be using as example data from this 2013 JAMA article. Now, this study is a so-called Advance 3 study. The hypothesis here is that if detection of cardiac arrhythmias was prolonged or delayed, this would actually allow non-sustained arrhythmia events to self-terminate, thus avoiding unnecessary deliveries of shock and antitachycardia pacing by the implantable defibrillator or ICD. Now, it has actually been reported in a number of studies that ICD therapies, that is, delivery of shock and antitachycardia pacing, whether it was appropriate or not, are associated with increased risk of death and worsening heart failure. So, interventions that spare such therapies are definitely something worth looking into. Now, in this study, the intervention being evaluated, that is, the use of prolonged detection programming of 30 to 40 intervals, was compared against the standard, which was the use of conventional detection programming of 18 to 24 intervals. So, in essence, with delaying or prolonging arrhythmia detection, non-sustained arrhythmia events are allowed to self-terminate, and thus lesser shocks and antitachycardia pacing will be delivered. Now, the primary outcome in this study is the total number of ICD therapies delivered for all episodes of arrhythmias. The results are shown in Table 2 of this article. Now, let us focus on the number of combined therapies. As you can see, this is count data. Now, as for the time component or the time interval, these patients were followed over a course of 12 months. So the total exposure per treatment arm contributed by each patient in patient years were recorded as well. Now, for purposes of exercise, we will convert the average therapy rate unit from per 100 patient year to per 10 patient year, so that the corresponding lambdas per treatment arm will be 10 times lower, thus making it easier to construct the probability distribution curve and appreciate its shape. But before we move forward with the example, we have to ask ourselves, is modeling the data using Poisson distribution appropriate? Now, there are three things to look at when assessing if the Poisson model can be used for a certain piece of data: the event X, the sample size N, and the probability P. Let's look at event first. Is the event of interest count data randomly distributed in space or time? In the study, the time interval is 1 year, and the event, which is the occurrence of shocks and pacing, occur in no fixed methodical fashion. That is, they occur haphazardly in that particular time period, because obviously no one knows when an arrhythmia requiring ICD fighting would occur. Thus, the answer to this question is yes. In terms of sample size, is the N large? This study was able to enroll 1,902 patients. Now that is quite a large number that makes usage of the binomial distribution formula very impractical. So the answer to this question is also yes. Now how about probability? Is the probability small? In the investigational group, the average rate of event occurring is 4.2 for every 10 patients in that 12-month-long time period. That occurrence is actually very infrequent. So the answer to this question is also yes. Now, here's the data that we need, which we arranged in another table. Our lambda here will be the average number of ICD therapies delivered per 10 patient year. We can compute that by dividing the number of therapies delivered by the exposure in per patient year, then multiplying it by 10. Now for the standard group, the lambda is 6.7. Now, what if we want to know the probability of having no shocks or overdrive pacing delivered per 10 patients over a 12-month period? Now here our x is 0, so plugging in the values to the Poisson formula, we get a probability of 0.0012. Now, how about in the intervention arm? The lambda in this case is 4.2, and asking the same question as previous, the probability of having no shocks or overdrive pacing delivered per 10 patients over a 12-month period is 0.0150. Now, this is a bit larger than that of the standard group, which is expected since the average number of times an ICD fires per 10 patients in a year in that group, that is, the lambda, is higher. Now, let's consider values of x other than 0. which are listed under the first column of this table. Our lambda here is the mean number of treatment deliveries per 10 patient years of the standard group, which is 6.7. The middle three columns of this table are the different terms in the Poisson distribution equation, and the last column lists the resultant probabilities corresponding to each value of x. As you probably might have noticed, the number of occurrences of an event, which is x, can take any positive integer value. The higher the count number, however, the more infinitesimally smaller the probability of such occurring. Now, like what was done in the binomial distribution video, if all of these resultant probabilities were graphed in a vertical bar graph, we would get something like this. This is the Poisson probability distribution for lambda equal to 6.7. The shape of this graph is actually not that of a symmetrical bell-shaped curve. It's actually quite subtle, but there's some skewness on the right. We do the same thing with the intervention group. The lambda value this time is smaller compared to the standard group. We only are up to x equal to 12 in this table because the corresponding resultant probability is already very small at this point. Plotting the data in a vertical bar graph, we get this. This is the Poisson probability distribution for lambda equal to 4.2. The right-sided skewness is a lot less subtle here compared to the probability distribution of the standard group. Now, what did we get from this exercise? Recall that the shape of the binomial probability distribution plot varies with the values of n and p. In the case of the Poisson probability distribution, the shape of the graph varies with the values of lambda, as you can see in this figure here. Notice how the shape of the graph evolves with increasing values of lambda. Now, let us do a comparison of the binomial and Poisson probability distributions. With the binomial distribution, the n and p would already be sufficient to specify it. The mean in this distribution is the product of n and p, and the variance is n times p times the complement of p. Now, with the Poisson distribution, on the other hand, knowing the lambda is sufficient to specify this distribution. The corresponding mean and variance is likewise the lambda. The standard deviation is simply the square root of the variance. Now, there's actually an interesting way in which these two probability distributions are related. Now, for those who went ahead and read textbooks on probability theories, you may already have encountered this mathematical relationship. Now, this is read as follows. The limit of the binomial distribution equation as the sample size n approaches infinity is the Poisson distribution equation. What this actually means to say is that as the n or the sample size increases with no upper bound, that is, towards infinity, the Poisson and binomial probability distributions approximate each other. Now, along with n approaching infinity, p has to approach 0 as well to effect approximation of the two probability distributions. Now, biostatistics textbooks will mention some conditions in which Poisson approximation to the binomial becomes appropriate. The product of n and p has to be less than 10. Now, with this, we should probably just assume that n is large enough and p is small enough to get a product of 10. Next, n has to be at least 20 and p has to be at most 0.05. This image here, which I obtained with permission from a blog post of Statistics at Home, the link of which is on the screen and in the description below, shows different impositions of the Poisson and binomial distributions depending on the values of n and p. Now, these graphs were generated by a statistical software called R. Now, notice at p equal to 0.05, the two distributions fairly approximate each other. Notice too how the approximation becomes even more appropriate with an increase in n and a further decrease in p. Now, let's try another example. Here's an old study that was published in 1990, the coronary artery surgery study, which was also used as an example in the textbook by Dawson and Trapp. Now, this study included 780 patients with mild or moderate stable angina or asymptomatic survivors of myocardial infarction who were randomized to receive either medical or surgical therapy. Now, each treatment group had 390 patients. Now, the investigators looked at quite a few outcomes here, but for our purposes, we are going to focus only on hospitalization frequency. Now, here is an excerpt of that article which tells us how many total hospitalizations occurred per treatment group over a 10-year follow-up period. Let's extract this data and present it in tabular form. In the medical group, there were a total of 1,256 hospitalizations dispersed over this 10-year period. On the other hand, the surgical group had 1,487 hospitalizations. Now, to get the average number of hospitalizations per patient over this time period, a number which is effectively our lambda, we divide the total number of hospitalizations by the number of patients in each treatment group. Now, for this example, let's just focus on the medical group, which has a lambda of 3.2. We want to know the probability that a patient in the medical group has 2 hospitalizations over this 10-year period. Now, plugging in the respective values, we get a probability of 0.209. Now, what if we want to know the probability that a patient in the medical group was hospitalized 2 times at most during this 10-year time period? And what if we want to know as well the probability that a patient in the medical group was admitted more than 2 times during the same time period? We could do one of 2 things. The first one is we solve for and tabulate the respective probabilities corresponding to the different values of x starting from x is equal to 0 up to the point where the value of p is small enough. Let's start with the first question. We want to know the probability that a patient in a medical group was admitted at most twice over a 10-year time period. Paying careful attention to the inequality symbol, we have to add up the respective resultant probabilities of x is equal to 0, x is equal to 1, and x is equal to 2 to get our desired probability. Now that desired probability, which is the sum of these 3 probabilities, is 0.380. Now how about the next question? Here, we want to know the probability that a patient in the medical group was admitted more than twice during the 10-year follow-up period. Now, basing on the inequality symbol that was used, we start adding the respective resultant probabilities, starting with x is equal to 3 all the way up to x is equal to 10. The desired probability then is 0.621. Now, just as what I discussed previously in the binomial distribution video, this method becomes quite tedious to do and very impractical at that when x is large. In such cases, we can carry out the second method, which is to make use of the cumulative Poisson distribution table. Actually, we could make use of statistical software as well, but this will be a topic for another video. Now, going back to the cumulative Poisson distribution table, or tables actually, well, these are tables that give all the computed cumulative probabilities beginning with x equal to 0 up to some specific number of occurrences of an event, given a particular value for lambda. Now, here's a screenshot of such table which I got from the textbook by Daniel and Cross. Now, since our lambda is equal to 3.2, we focus on this section of the table. First, we wanted to know the probability that x is less than and equal to 2. Now, this particular example is already quite convenient for us because what it is asking for is the sum of the respective probabilities of x equal to 0, x equal to 1, and x equal to 2. Now, since this is a table of cumulative probabilities, we simply look for our lambda, which is 3.2, our x, which is 2, look for the intersection, and there you have your desired probability, which is actually the same as the one that we computed for earlier. Now, how about with the next example? What we basically want to find out here is the sum of the respective probabilities of x is equal to 3 all the way to x is equal to 11. So in actuality, we could also express a probability that x is more than 2 as a probability that x is more than or equal to 3. Now, if we were to place some sort of cutoff line, we could actually place that cutoff line right here. So essentially, we've now divided the whole into 2 mutually exclusive groups, namely x is equal to 2 and less, and x is equal to 3 and more. Now, with that thought in mind, we can look for the complementary probability of the expression on the right. In this case, it is 1 minus the probability of x equal to and less than 2. And we already know that the probability of x equal to and less than 2 is 0.380. By subtracting it from 1, we get 0.620, slightly different from the computed answer of 0.621 from earlier, but we could actually blame that on the rounding off. Now, to close this video, let's quickly assess the Poisson distribution to see if it satisfies the axioms of probability. Let's refer to this table here, which we use for our second example. Notice that all the resultant probabilities are non-negative and between 0 and 1. Summing up all these probabilities, we basically get a value of 1. With that, it also follows that each x occurrence is mutually exclusive.